Mm. Well, today I am here to give a presentation for 2000 AIChE annual meeting. Uh, my topic is simulation of rotating ring disk electrode and the effects of ionic migration in presence of homogeneous oxidation of ferrous in 0.01 molar H2SO400 oxygen pressure, and I am going to present the disk results only. Let me introduce myself. I am Dr. Shishendu Guha. I am working as Deputy General Manager in Process Division of Engineers India Limited, New Delhi, India. And my company works in the field of oil and gas industry. Now, let me quickly go through the slides so that the presentation is made a stipulated time of 15 minutes. Now, what is a RRT or rotating ring disk electrode? The rotating ring disk electrode, the picture of a rotating ring disk electrode is given here. It consists of a disk, a gap, and a ring. The disk and the ring are all concentric. Gap is made of generally PTFE. The disk and the ring are made of platinum. Now, my research work is on the usage of this rotating ring disk electrode for finding out the effects of ionic migration in presence of kinetic complications of oxidation of ferrous in sulfuric acid under oxygen pressure. Now, as I have shown, the rotating ring disk electrode is a very convenient arrangement of two working electrodes in a common cell. Concentric rotating electrode structure is very uh, easy to fabricate. It is available commercially. Popular tool for study of electrochemical reactions because the hydrodynamics of the system is very well established. RRD has a very unique feature that it can detect solution phase intermediates generated in situ in the electrochemical reactions. The working electrodes interact through potential distribution. The counter electrode is utilized. The ring and the disc is operated potentiostatically with the current from each electrode being collected by the counter electrode. So the disc and the ring can be operated together, current being collected by the counter electrode. The disc potential and the ring potential are measured in a reference electrode. Now, the rotating ring disk electrode is such a device which can be used to produce a species which is not existing in the bulk solution, and that can be collected by the ring electrode. So it can detect solution phase intermediates which is generated in situ in any electrochemical reaction. Intermediate so generated in the disk reaction may undergo homogeneous chemical reaction in the solution. That's what we have considered in the present. Now, the key design parameters of any rotating ring disk electrode is its collection efficiency and the transit time. Collection efficiency is the amount of material which is detected at the ring to the amount of material produced at the disk, which I have explained. And the transit time gives the actually it is average time required for material produced at the disk electrode to travel across the gap between the disk and the ring electrode. So it is the time to reach the ring electrode from the disk electrode for the ions. I'll give you a setup uh, diagram of a rotating ring disk electrode in figure 2. This is figure 2 where I've given the a RRD setup. There are two working electrodes, the ring and the disc. There is one counter electrode, there is one reference electrode, and two more ports are there for purging of gas and venting out gas. Now, most of the past research work on RRD has been restricted to situations where migration of ionic species had been neglected because of presence of excess of supporting electrolyte. What is supporting electrolyte? Supporting electrolytes are those electrolytes like sulfuric acid, hydrochloric acid, which when used in excess in electrochemical reaction leads to enhancement of the conductivity of the solution and the uh, initial gradient becomes nil. So the migration mode of transport for these situations becomes insignificant. But there are many situations where the supporting electrolyte cannot. Now, there are the important examples are the anodic dissolution process, metal deposition from a binary salt solution, and metal deposition from a solution partially supported by acid. In these situations, migration plays an important role because we cannot use supporting electrolyte or the supporting electrolyte concentration is very low. And due to presence of this migration mode of transport, the currents at the electrodes. Now, this is what I have already spoken. Now, let me tell about the system I have considered for simulation. The system chosen for simulation is 0.01 molar solution of ferric sulfate with very little 0.01 molar sulfuric acid as supporting electrolyte. Oxygen pressure and temperature are considered as 150 kPa and 298 Kelvin, and the RRD rotation rate is 1000 rpm. Two cases have been considered. One is presence of migration, and another is absence of migration. Now, the mathematical model I am going to show. The system is the disk reaction. In the disk reaction, the ferric ion, which is transported from the bulk to the disk, is converted to ferrous. Ferric is A, ferrous is B. Then the B, which is generated at the disk, is transported to the ring, and there is homogeneous oxidation of B, A also. The homogeneous reaction rate constant is given as first order rate constant rate equation, that is minus d ferrous concentration by dt equal to k1 considered of ferrous. Now this is the mathematical model. The absence of migration case can be given as these equations as the transport equations. These are the things which are available in my literature. So one may refer it. Now the boundary conditions are these that at time t is equal to 0, CST is equal to 0, CST is equal to 1. All these things have can be understood just by referring these slides when one is interested. Now The mathematical model for the final equations which have been solved in this case are this. So the dynamic concentration profiles can be calculated using these equations. So these are big equations. So I am not going to describe the modeling part of it because it will not. It's not possible to describe all these things in this small time. So I will go through these equations with the boundary conditions. Basically, there are a set of equations for the presence of migration case as well as absence of migration case, and with boundary conditions which are solved to ascertain the effect of migration. So I will go quickly through these slides. Now, this equation gives the current which is obtained at the disk, and the comparison with the Levich equation also. Now I will go to the results. Now all those equations have been solved using a numerical method, that is finite difference method, and the solutions give me some interesting results. Now figure 3 gives me the dimensionless profile of A, that is spheric, with the distance from the disk, and it is can be said that the accuracy of the simulation is very good because the steady state profiles which I have got nearly matches with the simulation results given by other researchers, which is approximate analytical solution, which is given by this equation. Now, if in figure 2 the concentration of A is plotted, the dimensional concentration of A is plotted with the dimensionless time, and the effect of migration is also visible. That is, the dimensionless concentration of A is always higher from T 0.02 and greater than dimensional concentration in absence of migration. So, the effect of migration is quite visible. Now, in the next slide, the concentration of A is plotted against the dimensionless normal distance. Here also the effect of migration is quite visible. Now, I will go quickly through these slides because of lack of time. The current obtained at the disk in presence of migration is lesser compared to the current in absence of migration, and the current calculated in this one matches very well in absence of migration case with the current which can be obtained using Levich equation. Now for the B, for the material which is generated at the disk, that is ferrous, the concentration profile with time, with dimensionless times are like this. So there is quite good amount of dependence of concentration with the uh, in presence of migration. For if concentration of B is plotted against the dimensionless normal distance, also we can see that in absence of migration case and vis-a-vis presence of migration case has quite considerable effect on it. Now, if the the dimensionless potential is plotted against the dimensional normal distance, that is the potential profile in presence of migration, is this one. There is considerable potential gradient, so it gives the effect of migration. Now, conclusions from this work, there are very interesting conclusions. The work presented has established that migration mode of transport is extremely important for analysis of electrochemical systems where supporting electrolyte cannot be used or its concentration is very low, and also in presence of kinetic complexities such as homogeneous oxidation reaction of ferrous ion in 0.01 molar sulfuric acid under oxygen. This work has indicated that concentration boundary layer thickness of limiting reactant ferric reduces appreciably when the magnesium mode of transport is present. That is available in those slides. It is also noticed that in presence of magnesium, steady-state limiting current suffers substantial reduction as compared to the steady-state limiting current in absence of magnesium. Yes, the accuracy of this simulation work may be highlighted from the fact that the simulated steady-state limiting this current in absence of magnesium is in very close agreement with the estimated Levitch steady-state limiting this current in absence of magnesium. It's found that the rate of oxidation of ferrous ions to ferric ion at all rate constant values is higher in presence of magnesium when compared with the rate of oxidation of ferrous ion in absence of magnesium. So we have got a plethora of uh, 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 dependencies of the magnesium. These are the notations. I will not go into the details of it. And so I will complete my presentation with this. Uh, so this is the reference, and it's a Levitch work. Okay, then because the time is less, it. Thank you.